Lesson 1. Discovering parts of an atom. Reading guide. Key concepts. Essential questions. What is an atom? How would you describe the size of an atom? How has the atomic model changed over time? Vocabulary. Atom. Electron. Nucleus. Proton. Neutron. Electron cloud. Inquiry. A microscopic mountain range? This photo shows a glimpse of the tiny particles that make up matter. A special microscope, invented in 1981, made this image. However, scientists knew these tiny particles existed long before they were able to see them. What are these tiny particles? How small do you think they are? How might scientists have learned so much about them before being able to see them? Early ideas about matter. Look at your hands. What are they made of? You might answer that your hands are made of things such as skin, bone, muscle, and blood. You might recall that each of these is made of even smaller structures called cells. Are cells made of even smaller parts? Imagine dividing something into smaller and smaller parts. What would you end up with? Greek philosophers discussed and debated questions such as these more than 2,000 years ago. At the time, many thought that all matter is made of only 4 elements: fire, water, air, and earth, as shown in Figure 1. However, they weren't able to test their ideas because scientific tools and methods such as experimentation did not exist yet. The ideas proposed by the most influential philosophers usually were accepted over the ideas of less influential philosophers. One philosopher, Democritus, 460 to 370 BC, challenged the popular idea of matter. Democritus. Democritus believed that matter is made of small, solid objects that cannot be divided, created, or destroyed. He called these objects atomos, from which the English word atom is derived. Democritus proposed that different types of matter are made from different types of atoms. For example, he said that smooth matter is made of smooth atoms. He also proposed that nothing is between these atoms except empty space. Table 1 summarizes Democritus's ideas. Although Democritus had no way to test his ideas, many of his ideas are similar to the way scientists describe the atom today. Because Democritus's ideas did not conform to the popular opinion, and because they could not be tested scientifically, they were open for debate. One philosopher who challenged Democritus's ideas was Aristotle. Reading. Aristotle. Aristotle, 384 to 322 BC, did not believe that empty space exists. Instead, he favored the more popular idea that all matter is made of fire, water, air, and earth. Because Aristotle was so influential, his ideas were accepted. Democritus's ideas about atoms were not studied again for more than 2,000 years. Dalton's atomic model. In the late 1700s, English schoolteacher and scientist John Dalton, 1766 to 1844, revisited the idea of atoms. Since Democritus's time, advancements had been made in technology and scientific methods. Dalton made careful observations and measurements of chemical reactions. He combined data from his own scientific research with data from the research of other scientists to propose the atomic theory. Table 1 lists ways that Dalton's atomic theory supported some of the ideas of Democritus. Democritus. Number 1. Atoms are small solid objects that cannot be divided, created, or destroyed. Number 2. Atoms are constantly moving in empty space. Number 3. Different types of matter are made of different types of atoms. Number 4. The properties of the atoms determine the properties of matter. John Dalton. Number 1. All matter is made of atoms that cannot be divided, created, or destroyed. Number 2. During a chemical reaction, atoms of one element cannot be converted into atoms of another element. Number 3. Atoms of one element are identical to each other, but different from atoms of another element. Number 4. Atoms combine in specific ratios. The atom. Today, scientists agree that matter is made of atoms with empty space between and within them. What is an atom? Imagine dividing the piece of aluminum shown in Figure 2 into smaller and smaller pieces. At first, you would be able to cut the pieces with scissors, but eventually, you would have a piece that is too small to see, much smaller than the smallest piece you could cut with scissors. This small piece is an aluminum atom. An aluminum atom cannot be divided into smaller aluminum pieces. An atom is the smallest piece of an element that still represents that element. Key concept check. What is a copper atom? The size of atoms. Just how small is an atom? Atoms of different elements are different sizes, but all are very, very small. You cannot see atoms with just your eyes, or even with most microscopes. Atoms are so small that about 7.5 trillion carbon atoms could fit into the period at the end of this sentence. Key concept check. How would you describe the size of an atom? Seeing atoms. Scientific experiments verified that matter is made of atoms long before scientists were able to see atoms. However, the 1981 invention of a high-powered microscope called a scanning tunneling microscope, STM, enabled scientists to see individual atoms for the first time. Figure 3 shows an STM image. An STM uses a tiny metal tip to trace the surface of a piece of matter. The result is an image of atoms on the surface. Even today, scientists still cannot see inside an atom. However, scientists have learned that atoms are not the smallest particles of matter. In fact, atoms are made of much smaller particles. What are these particles, and how did scientists discover them if they could not see them? Thompson, discovering electrons. Not long after Dalton's findings, another English scientist named J.J. Thompson, 1856 to 1940, made some important discoveries. Thompson and other scientists of that time worked with cathode ray tubes. If you ever have seen a neon sign, an older computer monitor, or the color display on an ATM screen, you have seen a cathode ray tube. Thompson's cathode ray tube, shown in Figure 4, was a glass tube with pieces of metal, called electrodes, attached inside the tube. The electrodes were connected to wires, and the wires were connected to a battery. Thompson discovered that if most of the air was removed from the tube and electricity was passed through the wires, greenish-colored rays traveled from one electrode to the other end of the tube. What were these rays made of? Negative particles. Scientists called these rays cathode rays. Thompson wanted to know if these rays had an electric charge. To find out, he placed two plates on opposite sides of the tube. One plate was positively charged, and the other plate was negatively charged, as shown in Figure 4. Thompson discovered that these rays bent toward the positively charged plate and away from the negatively charged plate. Recall that opposite charges attract each other, and like charges repel each other. Thompson concluded that cathode rays are negatively charged. Parts of atoms. Through more experiments, Thompson learned that these rays were made of particles that had mass. The mass of one of these particles was much smaller than the mass of the smallest atoms. This was surprising information to Thompson. Until then, scientists understood that the smallest particle of matter is an atom. But these rays were made of particles that were even smaller than atoms. Where did these small, negatively charged particles come from? Thompson proposed that these particles came from the metal atoms in the electrode. Thompson discovered that identical rays were produced regardless of the kind of metal used to make the electrode. Putting these clues together, Thompson concluded that cathode rays were made of small, negatively charged particles. He called these particles electrons. An electron is a particle with one negative charge. Because atoms are neutral, or not electrically charged, Thompson proposed that atoms also must contain a positive charge that balances the negatively charged electrons. Thomson's atomic model. Thomson's atomic model. Thompson used this information to propose a new model of the atom. Instead of a solid, neutral sphere that was the same throughout, Thomson's model of the atom contained both positive and negative charges. He proposed that an atom was a sphere with a positive charge evenly spread throughout. Negatively charged electrons were mixed through the positive charge, similar to the way chocolate chips are mixed in cookie dough. Figure 5 shows this model. Reading check. Rutherford, discovering the nucleus. The discovery of electrons stunned scientists. Ernest Rutherford, 1871 to 1937, was a student of Thompson's who eventually had students of his own. Rutherford's students set up experiments to test Thompson's atomic model and to learn more about what atoms contain. They discovered another surprise. Rutherford's predicted result. Imagine throwing a baseball into a pile of table tennis balls. The baseball likely would knock the table tennis balls out of the way and continue moving in a relatively straight line. This is similar to what Rutherford's students expected to see when they shot alpha particles into atoms. Alpha particles are dense and positively charged. Because they are so dense, only another dense particle could deflect the path of an alpha particle. According to Thomson's model, the positive charge of the atom was too spread out and not dense enough to change the path of an alpha particle. Electrons wouldn't affect the path of an alpha particle because electrons didn't have enough mass. The result that Rutherford students expected is shown in Figure 6. Reading check. The gold foil experiment. Rutherford students went to work. They placed a source of alpha particles near a very thin piece of gold foil. Recall that all matter is made of atoms. Therefore, the gold foil was made of gold atoms. A screen surrounded the gold foil. When an alpha particle struck the screen, it created a spot of light. Rutherford students could determine the path of the alpha particles by observing the spots of light on the screen. The surprising result. Figure 7 shows what the students observed. Most of the particles did indeed travel through the foil in a straight path. However, a few particles struck the foil and bounced off the side, and one particle in 10,000 bounced straight back. Rutherford later described this surprising result, saying it was almost as incredible as if you had fired a 38-centimeter shell at a piece of tissue paper and it came back and hit you. The alpha particles must have struck something dense and positively charged inside the nucleus. Thomson's model had to be refined. Rutherford's atomic model. Because most alpha particles traveled through the foil in a straight path, Rutherford concluded that atoms are made mostly of empty space. The alpha particles that bounced backward must have hit a dense, positive mass. Rutherford concluded that most of an atom's mass and positive charge is concentrated in a small area in the center of the atom called the nucleus. Figure 8 shows Rutherford's atomic model. Additional research showed that the positive charge in the nucleus was made of positively charged particles called protons. A proton is an atomic particle that has one positive charge. Negatively charged electrons move in the empty space surrounding the nucleus. Discovering neutrons. The modern model of the atom was beginning to take shape. Rutherford's colleague, James Chadwick, 1891 to 1974, also researched atoms and discovered that, in addition to protons, the nucleus also contained neutrons. A neutron is a neutral particle that exists in the nucleus of an atom. Bohr's atomic model. Rutherford's model explained much of his students' experimental evidence. However, there were several observations that the model could not explain. For example, scientists noticed that if certain elements were heated in a flame, they gave off specific colors of light. Each color of light had a specific amount of energy. Where did this light come from? Niels Bohr, 1885 to 1962, another student of Rutherford's, proposed an answer. Bohr studied hydrogen atoms because they contain only one electron. He experimented with adding electric energy to hydrogen and studying the energy that was released. His experiments led to a revised atomic model. Electrons in the Bohr model. Bohr's model is shown in Figure 9. Bohr proposed that electrons move in circular orbits, or energy levels, around the nucleus. Electrons in an energy level have a specific amount of energy. Electrons closer to the nucleus have less energy than electrons farther away from the nucleus. When energy is added to an atom, electrons gain energy and move from a lower energy level to a higher energy level. When the electrons return to the lower energy level, they release a specific amount of energy as light. This is the light that is seen when elements are heated. Limitations of the Bohr model. Bohr reasoned that if his model were accurate for atoms with one electron, it would be accurate for atoms with more than one electron. However, this was not the case. More research showed that, although electrons have specific amounts of energy, energy levels are not arranged in circular orbits. How do electrons move in an atom? Key concept check. How did Bohr's atomic... The modern atomic model. In the modern atomic model, electrons form an electron cloud. An electron cloud is an area around an atomic nucleus where an electron is most likely to be located. Imagine taking a time-lapse photograph of bees around a hive. You might see a blurry cloud. The cloud might be denser near the hive than farther away because the bees spend more time near the hive. In a similar way, electrons constantly move around the nucleus. It is impossible to know both the speed and exact location of an electron at a given moment in time. Instead, scientists only can predict the likelihood that an electron is in a particular location. The electron cloud shown in Figure 10 is mostly empty space, but represents the likelihood of finding an electron in a given area. The darker areas represent areas where electrons are more likely to be. Quarks. You have read that atoms are made of smaller parts: protons, neutrons, and electrons. Are these particles made of even smaller parts? Scientists have discovered that electrons are not made of smaller parts. However, research has shown that protons and neutrons are made of smaller particles called quarks. Scientists theorize that there are 6 types of quarks. They have named these quarks up, down, charm, strange, top, and bottom. Protons are made of 2 up quarks and 1 down quark. Neutrons are made of 2 down quarks and 1 up quark. Just as the model of the atom has changed over time, the current model might also change with the invention of new technology that aids the discovery of new information.